The next problem was sort of something that the theorists didn't like very much, and this time, usually they're wrong, but this time it turned out they were right. Like our radio station, they started thinking about how are atoms put together. Now the original idea was that atoms were so-called pizza-type atoms, where the electrons were like the pepperonis in a pizza. You know, you imagine that they're just sort of sitting and they're distributed. But actually, they had a reason for that. They didn't like the idea that electrons would circulate around the central nucleus in the atom, which was okay until somebody named Rutherford discovered that there was a nucleus to the atom, a very small thing, much smaller than the atom itself. That was an experimental discovery in 1911. Big problem now because the atom size was roughly known. I just told you that the atom size is 3 orders of magnitude bigger than the nucleus size, so that's why you're all electric field. So the nucleus of the atom was discovered in 1911 by Rutherford, and so no matter should exist at all. Basically what should happen is, this is accelerated, right? In circular motion, we have an acceleration which pulls towards the center, the centripetal force, which is pulling towards the center. If you don't have acceleration, things travel in straight lines. So this is accelerated. It should give off a lot of electromagnetic radiation. In fact, in the classical regime, when we build an electron accelerator, that does give off an incredible amount of radiation. Usually in X-rays, it's called synchrotron radiation. It's used exhaustively for a study of materials today, and so on. So it's true. Electrons going in circles give off radiation. However, in atoms, somehow they don't. Because if they do, you know, in an accelerator, you keep pumping power into it. But in an atom, there is no power. So this thing should just spiral and spiral and spiral down to the center and annihilate, and there would be no matter, nothing. So there was no. So now we have the kind of problem that really bothers physicists, namely that there's no reason for there to be any matter at all. If you think we've solved that problem, by the way. So Niels Bohr discovered how the quantum theory could be applied to the atom. And he discovered it as soon as the nucleus was discovered. Inspired guesswork, I would say. He made a picture of the atom that consisted of the nucleus and atoms going around in circles or other shapes, but we'll use circles for now. And his statement was, well, they go around in circles, but they don't radiate. I mean, you know, you say they radiate, I say they don't radiate. That's it. There's a German word for this called Ansatz, which means it basically means you just throw something down on the table and say that's it. You know, and this is what it is. There were several of them. Einstein used this all the time. He said, speed of light is constant in all frames. Bang, that's it. You know, check it out. You know, this thing is a particle in a wave. Oh, that, check it out. You know, these things go around in circles and they don't radiate. Well, okay. The orbits are stable, said Bohr, unless they jump between different levels. That says that we should see photons coming out with specific frequencies. You do. If you look at the frequency of radiation emitted by a hot atom, you'll see lines instead of a broad spectrum as a function of the frequency of the radiation coming out. You see these very sharp lines. That's called spectroscopy. And the radii, he said, are set by this formula, which he made up, which is the radius is a number, 1, 2, 3, 4, 5, times this famous Planck's constant here, divided by 2 pi times the momentum. And momentum is set by the circular motion equation. So there's no continuous radiation. And this determines most of atomic physics, so it's probably worth an animation. I also really like this animation. So we'll give it, boom, there comes a, oh, this. You have your electron going around, and I'm going to put in a high energy photon coming in. Boom! There, so the thing jumps up, now it decays, and little photons come off. Here comes another photon. Oh, there it comes. Wow, it seems to always go to the same place. Well, that's not what happens in reality. In reality, you can't define the place that well. But anyway, so you get the idea, and most of you have probably heard of this. because it's very popular in chemistry courses. It's discussed extensively in popular works. And it's the Bohr model of the electron, of the atom. It also makes no sense at all. So now we have things that make no sense at all but seem to work. And that was the situation we were in let's say, up till about 1920. Okay, there's a practical application of the Bohr, besides all the chemistry you know, which I like very much, which is the atomic clock. This picture looks like it was written in 1950. In fact, this is a function of the fact that I got it by emailing myself something from the Xerox machine. This picture was in the Physics Today of this month in an article by a guy named Camparo on the atomic clock. And atomic clocks are very important. They're the way we keep time now. There's an atomic clock on every GPS satellite. It turns out that GPS satellites would drift with respect to the time on the ground by quite a bit based on relativity, the fact that they're at a different gravitational potential than what's than down on the Earth. They would drift by 5 microseconds every 3 hours, which is a lot in the short time world. Microseconds are long in particle physics or in any kind of atomic physics, actually. So they need something a lot better to compare with, and they compare with these atomic clocks. An atomic clock works like this. You shine a light through a cavity full of some gas, in this case it's something called rubidium, and it makes one of these quantum hops if you have the right frequency. So you adjust the frequency of the light until you get until suddenly the intensity coming out goes down because you've absorbed some of the energy out of that beam. When that happens, you feed that back into your radio system. Your clock system is controlling your clock, and change the frequency that's controlling the clock by a little bit, which also changes the light frequency, and you put that into a feedback connection, and it's this hop between these two levels that determines the frequency, which is frequency then tells you exactly how to translate that into time. You use the speed of light, which is very well known, and you can turn the frequency into time. So a hopping Bohr level sucks power out of this light beam. So and there's one of these on every GPS satellite. And there are many other applications to atomic clocks. They're one of the reasons we have such precision knowledge of